Everyone, my name is Lakshman Purbe, and this is my lab report for oscillations. The purpose of this lab is to compare the observed motion of the mass attached to a spring with its predicted motion. In this lab, we'll be using Tracker to track the motion of the oscillating object, and then using VPython on GlowScript to build a computational model. The overview of the results indicate that the predicted and the observed motions were quite similar, and the change in the overall energy was 0. The fundamental principles of the lab are as follows. We use the momentum principle, which states that the net force is equivalent to the change in momentum over time. And the energy principle, which states that the change in the internal energy of a system can be quantified as the work done on the system by the surroundings and the microscopic heat transfers between the system and the surroundings. In this experiment, we'll be studying 3 different kinds of energy: kinetic energy, gravitational potential energy, and spring potential energy. Spring potential energy, which is the elastic energy associated with the compression and expansion of a string, and it's indicated by U equals 1/2 k delta x squared, where k is the spring coefficient, and delta x is the difference between the relaxed and the stretch length. The gravitational potential energy, which is the energy associated with the position of an object, which is U equals mgh, and kinetic energy, the energy associated with motion, which can be quantified as kinetic energy equals 1/2 mv squared. In this experiment, we define the system to be the earth, spring, and the mass. The forces acting on the system are as the spring force and the gravitational force, and since we include everything in the system, there is no work done on the system by the surroundings, and there is no heat transfer, so the change in internal energy is 0. Here's the overview of the results. After tracking the motion of the object of the mass on Tracker, we see that the mass follows an oscillatory motion in its x and y components. And we use this motion to calculate the period of this oscillatory motion. In the computational model, we begin by inputting the mass, which is 0.402 kilograms, the initial position we get from the Tracker data, and we begin by defining our constant. We define the gravitational constant and the spring constant, which we get from the period formula. We rearrange t equals 2 pi square root m over k to get k equals 4 pi squared over m. Using the same formula k L minus L naught, we use our defined values to calculate L naught, which we get to be 0.123. We then specify the vector L, where L is the difference between the ball's position and the spring's position, L hat, which is the unit vector that is L over the magnitude of L, and the S, the difference between the magnitude of the L and the L naught. We then continue to define the energies of the system, where the kinetic energy is 1/2 mv squared, the potential energy for gravitational potential energy is mgh, the spring potential energy, which is 1/2 ks squared, and the total energy being the sum of the 3. We define the calculation loop to be as follows. We define the gravitational force to be the vector mg in the negative direction, the spring force, which is negative ks times the L hat, which indicates the direction, and the net force, which is the sum of the 2 forces. Using the momentum principle, we update the ball's velocity, where ball's velocity is the final velocity equal to the initial velocity plus f net over m times delta t, and the position, which is ball's initial position plus ball's velocity times time. Then we update the spring to keep track of the spring, and we then calculate the energy changes, where delta k is the final kinetic energy minus the initial kinetic energy. The final potential energy is the final potential energy minus initial potential energy. The spring potential energy is the final spring potential energy minus initial spring potential energy, and delta E, which is just 0. Here is the results of the experiment. We can see that the model and the experimental data are quite similar. When considering the y position, we see that the model predicts a little more the extreme ends, the minimum and the maximum values. However, the overall pattern is that the overall period and the overall shape and the trend of the pattern of the graph tends to be the same. Since these graphs were not perfect, there were sources of error in the experiment, which could have been the incorrect tracking of the motion in Tracker and the incorrect calibration of the axes and the length in Tracker. We believe the energy principle was satisfied because the total sum of the kinetic energy, the potential energy, and the spring potential energy added to 0. Since we included everything, which included the earth, spring, and the mass in our system, there were no surroundings, and the work done on the system was 0. Therefore, the changes in the internal energy were also 0. The average period we calculated was for the x was 1.773 seconds, and the average period we calculated for the y was 1.899 seconds. We did this by calculating the period in for 3 periods and dividing to get the average period. While the differences in these periods is not that significant, this difference can lead to differences in our calculated spring constant and then overall, as a result, the spring potential energy. We believe that these differences can be attributed to the errors in tracking of the mass due to distortions in the video. Thank you.